This is a heating curve for water. So again, we've got temperature on the y-axis is a function of heat added. So if we started with ice at minus 25 degrees Celsius and we start adding heat, the temperature would go up until it started melting. Then all the heat that's added goes into the melting process. The temperature doesn't go up until all of it's melted. Then the temperature starts to go up until it begins to boil. Then we see the temperature remains the same until all the water has boiled, and then the gas will increase in temperature. So we can calculate the amount of energy needed for each of these processes. Each straight line segment is going to be a separate calculation, and then we add them together. Here's a conceptual question. I did this with my Tuesday, Thursday class. It didn't go very well, so we're going to skip that. Calculate the amount of heat needed to take 1 mole of ice at minus 25 degrees Celsius to steam at 125. So this is the picture that we just looked at, this picture. But given on an exam, you're not going to be given the picture, so you kind of have to draw your own picture. So anytime you have a question like this where you have temperatures changing and states changing, you want to sketch a little heating curve. So here's the temperature, and here's heat being added. And so here I'm starting with ice at minus 25. As I heat up the ice, the temperature will increase until it starts to melt. And for water, that's going to be 0. At that point, it's going to keep melting until it's all liquid. Then the temperature can go up again until it starts boiling. It boils at 100. And then the temperature can increase again, and we're going to end up at 125. So I have to do a separate calculation for each line segment. So I'm going to number them 1, 2, 3, 4, and 5, so we can try to keep them straight. When we're heating things up, the equation we use is Q equals mc delta T. And when states are changing, we're going to use either the heat of vaporization or the heat of fusion to calculate the amount of energy. So the first line segment, we have ice going from minus 25 to 0 degrees. Q equals mc delta T. We're talking about 1 mole of ice. 1 mole of ice is equal to 18.02 grams. So I've got 18.02 grams of ice, and then I need the specific heat capacity. Here I've been given steam, water, and ice. I want to use the one for ice. So that's 2.09 joules per gram degrees Celsius. And then the temperature change, I'm going from minus 25 to 0. Final minus initial. The final temperature is 0 minus the initial temperature. And so I can calculate that. $941.5 joules. The calculation for line segment 3 and 5 are going to be very similar. The mass hasn't changed. But for line segment 3, I have liquid water, so I'm going to use the heat capacity for liquid water. And the temperature change here is going from 0 to 100. So that's 100, the final, minus the initial. And then down at the bottom here, for that 5th line segment, I've got steam, 2.01 joules per gram degrees Celsius. And the temperature there is going from 100 to 125. 125 minus 100. I know 5.5 joules. Number 2 is the heat of fusion. This is where we're melting, and so we're just going to take the number of moles. So I have 1 mole of water, and I'm going to use the heat of fusion, 6.02 kilojoules per mole. Just doing dimensional analysis there, and that gives me 6.02 kilojoules. And for number 4, I also have 1 mole of water. And now I'm boiling it, so I'm going to use the heat of vaporization. So 40.7 kilojoules. So I've got 5 answers right now. And some of them are in kilojoules and some of them are in joules. So I need to convert them all to the same. I'm going to pick kilojoules. So if I convert 941.5 joules, I get 0.9415 kilojoules. And this one in the middle, 7,532. That's going to be 7.532 kilojoules. And this one is going to be 0.9055 kilojoules. So I can add those up, 0.9415 plus 6.02 plus 7.532 plus 40.7 plus 0.9055, and the total is 56.099 kilojoules. 56.1 kilojoules. I know, right? It's ridiculous. This is one of those problems that all of the individual pieces are quite simple, but putting them together gets very messy. And if you're not on top of, if you don't write things out well, it can go wrong so easily. But I can pretty much guarantee there will be a question like this on the next exam. This one was going from a cold solid to a hot gas, but you could go any anything in between. You could start with is cold ice and just go to it finishes melting at 0. Or you could go to room temperature, or you could go from here to there, or you could start at the other end and cool it down. Yeah, going back, the energy is the same, it's just a different direction.
Exactly.
Yeah. So if you're cooling something, the temperature changes and everything can get kind of messy. And so what I would recommend, like if we were going from this point backwards, I'd recommend calculating it forwards and then changing the sign. And that way you don't have to deal with a whole bunch of negatives. But there you go. Those are fun.